Alright, good morning guys. Today we're going to look at cubic functions, and in these cubic functions we are going to look at if they give you the question in a derivative function and then they ask you questions. Okay, so I hope you are ready for your paper on Friday. So there's a question they are giving us. They are saying that the graph of y equals to f prime at x, where f is a cubic function, is sketched below. So you have the question, and they say use the graph to answer the following questions. For which values of x is the graph of y equals to f prime at x decreasing? So now when we say this graph here you are seeing is what we call y is equals to f prime at x. You see? So this graph is what is called y equals to f prime at x, and they're asking you where is it decreasing. So for you to know where it is decreasing, this graph has got a turning point, it's a parabola. Where is the parabola decreasing? So you can see from here, moving up to the turning point, it is increasing. And then from here, moving out down, is decreasing in terms of the slope, okay? So if you are even a driver and you're driving from here to here, you need to increase in terms of acceleration. And when you are going down here, you can put your car on a neutral and the car will come here. So it's decreasing in terms of speed. You can't go with a high speed here from the hilltop. So here you are decreasing, and here you are increasing. So but then you need to find out what is the x value of the turning point. So you add this x value and that x value and you divide it into 2. The number you get here is also called the axis of symmetry. The x value of the turning point of the parabola is also called the axis of what? Symmetry. So it's minus 4 plus 1, which is minus 3. Then you divide it by 2. So the x value of the turning point is negative 3 over 2. Then now we are asking where is it decreasing? It is decreasing from that point to this side of the turning point. So now you can say the graph of y is equals to f prime at x is decreasing at x is greater than negative 3 over 2, because from here we have all the numbers moving this side to the x are greater than that negative 3 over 2. So that is the answer or the solution to the question that they have asked you. I hope you understand the question. Now the next question says, when you look at 4.2, this says at which values of x does the graph of f have a local minimum? Give reason for your answer. So in order for us to know where is a local minimum, we need to understand goes on what goes on the graph of the parabola, which is also known as the derivative function of f. So now let's go to the derivative function. They give us in this order. In a parabola, when you have this graph sketch, it means the value of a is negative, okay? So when you take that into drawing a mind picture of f, you get this shape here. Okay, because if a is negative, remember in cubic function, if a is negative, you get a graph which is concave up and then concave down, or which we say minimum before maximum. So looking at these two numbers, one can say that x is equals to negative 4 from those two stationary points is where we will have our local minimum. X is equals to negative 4. So on the cubic function, those x values on the x-axis of the parabola refers to the stationary points. So if in the question they ask you to write down the coordinates of the stationary points, or the x-coordinate of the stationary point, you will simply say x is equals to -4, or x is equals to that one that you are seeing there. S is equals to -4, or s is equals to 1 when you are writing the stationary points, because this is the derivative function of the cubic function, which is f at x. So these numbers that you are seeing on the x-intercept here on the parabola is also the stationary or the turning points of the cubic function. I hope you understand what I'm talking about here. So that's where we are now. So the graph will have a minimum at -4. But the reason, as I picked up here, so that the shape of the derivative function depends on the coefficient of x squared, which is negative in this case. Our coefficient is negative, that's why we got that shape. This means that the graph of f will have also a coefficient of s cubed, which is also negative, and therefore the graph will have this shape, which is minimum before maximum. So if you've got two turning points and one is -4, it means it will come first before the maximum turning point comes. That's why we say x is equals to -4 has a local minimum. So we're done with that. We can ask questions. If you don't understand, we will explain it back to you again. Now let's look at the next question, which is question 5 from this. In the sketch below, the graph of y is equals to ax squared plus bx plus c represent the derivative f prime, of which f is a cubic function. So this is what they have given you. So they always will sketch the derivative function for you, and they will trick your mind to see whether you understand when you to translate the derivative function to a cubic function. So remember, the derivative function can be like a daughter to the cubic function. So you must look at those two pictures. When the derivative function is a parabola, which is a sad face, you see the graph going down. It means when you are sketching the original graph of the cubic function, it will be a minimum before maximum. A minimum before maximum. In other terms, you say concave up and then concave down. Okay. But if the derivative function is a smiling shape, which means it is open up, like in this question, then you are going to have a concave down first before concave up. That means you are going to have maximum before a minimum turning point in that graph. Okay. So now let's look at the question. So write down the coordinates of the stationary points of f. Like I did tell you, when they give you the derivative function, they can always ask you to write down the stationary points, or the stationary points is the same as the turning points. So now you just look no further. Go to the graph that they have given you, which is this one in our face now, and then you choose the numbers that are on the x-axis. Okay. So the stationary points here, one will say x is equals to this one, or s is equals to 2. So that is exactly what I've done here. We have this graph. Our stationary points are these numbers when you translate to the cubic functions. Okay, from the derivative function, whatever x-intercepts they give you on the parabola is your stationary point on the cubic function. I repeat. So when they ask you to write a cubic function stationary point, we say x is equals to 1 or x is equals to 2, like we see here. Now, the next question says we must state whether each stationary point in question 10.1 is a local minimum or local maximum, and we must substantiate our answer. So now you got two stationary points here, which is 1 or 2. So now for you to know, you need to take the daughter the shape, like I'm saying, this is a daughter. The parabola is born out of the cubic function. So the cubic function is f, and the derivative function is f prime at x, which is the parabola. So if I know the daughter, it is easy for me to tell who the mother is. So it is smiling. That means A here is positive. From the graph that is given, A is positive. And then when I'm going to draw the cubic function using a positive value of A, then it means I must have maximum turning point before minimum turning point. So looking at this number 1 and 2, 1 comes before 2. So you will say 1 x is equals to 1 has a maximum and x is equals to 2 has a minimum. Reason is that when we look at y is equals to ax squared plus bx plus c, we say the coefficient of x squared here, which is a, is positive. And this means that f at x will also have a maximum before a minimum turning point, because a in the cubic function is also positive. Therefore, 1 comes before 2. So 1 will be the maximum turning point and 2 will be the minimum turning point. So that is how I gave my explanation. You can also deduce and come up with your own explanation, but this is how I believe it should look like. Now, when I have 5.3, they are asking you to determine the coordinates of the point of the x coordinate of the point of inflection of f. Now, when we talk about point of inflection in cubic function, we are looking at where concavity is changing shape. Concavity is changing shape. If I'm looking at this graph, I'm looking at where this graph is changing shape. It's a halfway here, this point here. This is what we call point of inflection, POI. Point of what? Inflection is changing way. So it's a halfway between the shapes that you are seeing. Okay. So in that case, now that I know the turning point here is 1 and the turning point here is 2, if I'm calculating point of inflection or x coordinates of the point of inflection, you simply take from the parabola. That is what you have. Let's deal with the parabola. You take this one. This one is the same as that one, and this 2 is the same as this 2 on the cubic function. Okay. So when I'm calculating point of inflection, I will add this plus this, and then I will divide it by 2. So point of inflection using the graph of the parabola is simply the x-intercepts when you add them and divide by 2. So that is your point of inflection. So x is equals to 3 over 2. X is equals to 3 over 2. That is your point of inflection. Okay. And then now we're looking at other question, which is hence or otherwise draw a sketch of f. Now the word hence in mathematics, guys, boys and girls, when you are given any sentence that precedes with the word hence, it means you must use your previous solution as your base line to solve the current situation. Okay. So now what do we know? We know our point of inflection is 3 over 2. Yes. So 3 over 2 means it's like 1.5. Okay, that is our point of inflection. We were told also that the graph is going to have a maximum turning point at 1. X is equals to 1. And a minimum turning point at x is equals to 2. So now when I translate it here, my 1 is here. So my maximum turning point, so I move up a bit, is not drawn to scale. I push it up and I put my point here. And then I also look at my other turning point, which is at x is equals to 2 here. So that is the minimum turning point. So the graph, the shape of the graph is that I know that since the graph of the parabola is smiling, then the shape of the original graph, which is the cubic function, must also have a maximum before a minimum turning point. So I have that picture in the mind. So I draw through the center of origin, since I was not given any y-intercept, but it must pass through this point here. You can put it anywhere. There's no y value of the turning point needed. You are only using the x value. So at this point here is 1. Then I move down to 2, and there's a turning point also there. This is the minimum turning point. Then the graph must go up. So that is the shape. So I have this shape, smooth curve, which is at maximum at 1 and minimum at x is equals to 2. So then that is it. You are finished with the sketch of the graph. Okay. So that's it. We shall continue our lesson later.